So if all of you can bring up a terminal, whether it is on Gordon or on your own laptop. First thing we're going to do is we're going to run through IPython. So everything's going to be IPython. And I'm using Python 2.7. So let's start out by what I'm going to do is make my window a bit smaller because one of the challenges of running with a Mac. Okay, so the first thing we're going to do is we're going to look at the functions inside of AstroML and how we can actually work out what they can do. So let's start out by just doing import AstroML. Okay. This just imports the package. If you want to look at what functionality is in there, we can do help AstroML. And this shows you that there's a few packages. The ones that are important for displaying are the algorithms, in particular the data sets, which are pulling down data sets from SCSS, from linear for moving sources. We've got distributions packages, which plots up various statistical distributions. We've got the plotting package, and we've got the statistics package. So let's look at one of these functions, or one of these functions, and see what it can actually do. And we'll start out by accessing the data. Okay. So if you from AstroML.datasets import fetch SDSS under fetch underscore SDSS underscore spectrum, this is the application that will actually fetch and download a spectrum. Okay. So the first thing we'll do is we'll look at what that spectrum or what that application, what the parameters are that it takes in. Yes. Thank you. And let me do that. Does that work? Is that easier for you to see? Okay, so let's look at the first thing. So this is fetch underscore SDSS underscore spectrum. So what this is going to do is download a spectrum from the SDSS website. So if you want to see what the parameters are that go into this function, you just put a question mark at the end. And this gives you effectively the doc, it gives you the doc string. So what is input into this is the plate number, which is the SDSS observes using these large aluminum plates where fibers are actually plugged into it, and each observation corresponds to a plate. We have an MJD, which corresponds to the mean Julian date, which is just the time of the observation. And we have the fiber, so there's 640 fibers within plugged into that plate, so we just have what is the fiber ID. And so those three numbers define a unique spectrum. So it's effectively telling you the observation, it's telling you the time of the observation, and it's telling you what fiber is being used within that observation, within those 640 individual fibers within the plate. So this gives you the parameters that are input. It also gives you data home, which is an optional capability that whenever we download something, you can cache it so that the next time you want to run it, and the next time you want to fetch the data, there's no point in actually pulling the data down. And this goes into a directory called data underscore home. And so it gives you the option to cache to disk. And this option cache to disk is set as a default to true. So if you download a spectrum, it gets stored on your hard drive. So if you download every SDSS spectrum, you're going to fill up your hard drive. So that gives me the parameters associated with this function. What happens if I actually want to look at the code itself? Then I just put two question marks at the end. And this gives me the actual code within the Python application. So you can see it's setting data home. It's calculating the target URL from the plate, the MJD, and the fiber. So all that's really doing is it's calculating an HTTP / etc. string that will point to a specific SDSS spectrum that it's going to download. And then the rest of this is just download with progress bar. Just means that if it's a large file, as it downloads, it will give you a progress bar telling you how far along you've got. Okay. So let's use this. So the first thing we're going to do, let's make this fit, is we'll put in the plate number. So let's do plate equals 1615. We'll put in the MJD, the modified Julian date. So MJD equals 53166. And we're going to try and type. Initially, we'll be typing most of this stuff, because then you can actually try it out and keep up at speed, rather than just doing a series of cut and paste, which is I don't find quite as useful. And then fiber equals the fiber number, and you can choose whichever fiber number you want. We'll choose 513. Okay. So that sets the 3 parameters. The next thing we want to do is to get the data. So we'll data equals fetch underscore SDSS underscore spectrum, giving it the plate, the MJD, and the fiber. Okay. And so that's downloaded that spectrum. You see it's fairly quick. If you want to look at what are the parameters associated with that data, with the data structure, you can just do dir on the data structure, and this shows you all of the attributes associated with that spectrum. What does it have? Well, it has here, you can see the wavelength. That's the wavelength array. We've got redshift. We've got the spectrum over here. We've actually got the rest frame of the spectrum. We've got a rebin spectrum. We've got the mask associated with it. And then there's other parameters, such as the coefficients for the principal component analysis, and so on. We'll use some of these as we go through here. But in general, what this is really just doing is downloading the FITS file and loading it into memory. So let's start out by actually looking at the actual spectrum. So if we want to do that, we need to import matplotlib, which we'll import as pylab. It's PL. We will make it interactive, so it will actually display for us, which is pl.ion. And then the next thing we're going to do is just to plot up what the spectrum looks like. So let's do pl.plot data wavelength. Let's pass that array in, comma, data.spectrum, and then we'll do -k. We'll put in the labels, which is pl.xlabel, and we're just going to do the labels for the first one just to make it look good. And you can see that it's actually it's using LaTeX for its actual text. And we'll do pl for y label. And the next thing we're going to do is just show to see the spectrum. And there we have so this is one downloaded spectrum from the SDSS with wavelength on the bottom and flux on the y-axis. Okay, is everyone fine with that? I mean, you should have all seen that, I guess, when Rick, you did a number of these sorts of things with Python. Great. Okay, so let's start. The next thing we can do, I wanted to show another way of plotting up data, because this kind of relates to some of the data models that you've been doing in terms of the galaxy formation model. So let's just plot up or show the ability to plot up a set of scatter plots. So let's import for later NumPy as NP. And now we're going to import a set of scattered plot data, which is just going to be the colors of standard stars from the SDSS. So From AstroML.datasets, we're going to import fetch underscore SDSS underscore S82 standards. And you might just want to cut and paste that. And we're also going to import from AstroML's plotting packages the ability to plot up a multi-scatter plot. So this is going to be able to plot X against Y, X against Z, Y against C. And it's going to give you an array of scatter plots. Okay? And this is the multi-density, and it plots all of the points as a density. Right. So the data for this is from fetch underscore SDSS underscore S82 standards. And this is going to, if I could spell it correctly, this is going to pull down scatterplot data. Small s, thank you. Okay. We're going to create an array, and this array is going to be of length 4 because we're going to do a series of color plots: U minus G, G minus R, G minus R, R minus I minus I minus C. And so the first thing we have to be able to do is to calculate and populate this array. So it's just an array of length, the number of data points, and dimensions 4, where those 4 correspond to the colors: U minus G, G minus R, R minus I minus C. In fact, this case is we're actually going to do, so we will just cut and paste this, and this will just calculate the set of colors. So this is just calculating for the 0th axis, it's just pulling out U and G and doing U minus G. For the next axis, we're doing G minus R. For the next one, we're doing R minus I. And for the last one, we're doing I minus C. So we now have an array which has length, the number of data points, and it has columns which correspond to each of the colors. So if I did colors.shape, then this is going to give me, what is that? It's 1,000,000 points, and for each point we have U minus G, G minus R, R minus I minus C. Okay. We will put in the labels for this. And then the next thing we're going to do is we're going to calculate the density that we're interested in. So this is just going to specify what the bin range is that we want to work with. So if for the U minus G, we want to go from 0, U minus G of 0 to U minus G of 3.5, and we want to do that in 100 bins. For G minus R, we want to go from 0 to 2 with 100 bins. R minus I is minus 0.2 to 1.8, and I minus C is minus 0.2 to 1. Again, all of those with 100 bins. So this is just going to set up the binning of the data for when we actually calculate the densities. So the last thing we want to do in terms of plotting up the densities is just to call the function from the plotting package which corresponds to multi-density that we just imported up here. So if we run multi-density, we have to input colors, we have to input the labels for the axes, and we have to input the binning. And the binning is it's an optional parameter, otherwise it will define its own binning for you. Bins. And when we do this, you should all have, in a second or two, a plot that looks like this. Does everyone have that? So what this is doing is it's showing you a sequence of scatter plots. And this kind of comes back to something that Tomas was talking about when he was describing when you have large densities of points. If you've done this plot purely by putting the points down, then what tends to happen is you'll have, if you have a handful of points, it works quite nicely. If you have 100,000 points, then it basically just blocks out everything, and you get no ability to distinguish what the density of the points are simply by plotting individual points. So one of the things, and there's functionality in the AstroML plotting routines to combine density plots, or in fact contour plots, with scatter plots. Because really what I want to be able to do is I want to focus on contours in high density regions, and I'd like to see the actual individual points in low density regions. And so that gives me effectively the best of both worlds, because if you just try these density plots in low density regions where there's only a handful of points, you just won't see it. You won't see any of the structure. So this is kind of in terms of a visualization aspect that is important to be able to show large dynamic range in your plots. Right? So there's some functionality inside of AstroML that allows you to combine contours and density plots. All right. So let's start out with using AstroML for working with data. And we'll do principal component analysis, we'll do independent component analysis, and then we'll do local linear embedding. So we'll start out by not just taking one spectrum, we'll pull in a series of spectra. And this is using data equals AstroML datasets, and it's fetch underscore SDSS underscore corrected underscore spectra. So what does this mean? It means we're going to fetch a set of spectra. The spectra that we're going to pull over are going to be corrected, which means they're all going to be shifted to their rest frame because they've all been measured at a range of different redshifts. We have the redshift, we shift everything down to its rest frame, and we pull down those spectra as a whole. And if we do data.shape on this, doesn't like it, but if we do dirs, data, right, let's see. Okay. So we are now, from this data set, we're going to pull out the spectra. Did everyone else have more success than me with this? Data. I don't know what's this. Okay. The next thing we're going to do is to extract out the wavelengths, which will write into an array called lam for the actual wavelengths. So this is just taking this input spectrum and it's computing the actual wavelengths associated with the spectrum, or with the spectra. And then we're just going to take the first 850 elements from each of these spectra. And we'll do this also for the wavelengths so that they both have the same dimensionality. So now if I do spectra.shape, I should have 4,000 spectra, each with 800 elements. And if I do lambda or lam.shape, then I should have 850 wavelengths. Right. Everyone okay with that? Cool. All right. So now we actually get to start using scikit-learn. So the first thing we're going to do is we're going to pull it in from scikit-learn. We're going to pull it in the decomposition package, and we're going to take a principal component package. This is randomized PCA. It only extracts out the first n eigenfunctions or eigenvectors from the data, and it does this to make it fast. We could have used standard SVD, or we could have used any of the standard PCA packages. Randomized PCA will actually take your data and it will subtract off the mean, and then it will run the PCA on it. so you don't have to worry about that. You do have to worry about it when we're reconstructing the spectrum. So we'll import randomized PCA. I said it's that typically SVD type approaches scale on the order of around n cubed. There are much faster approaches that, there's a very famous one by Budavari et al., which has a very nice streaming algorithm, which allows you to do this for online applications. And so you can incrementally update your principal component analysis, and it really is quite a remarkable algorithm. Is that okay? Yeah, actually, we use it actually a lot. So let's also calculate the mean spectrum because we're going to plot it in a minute. So the mean spectrum is just taking the input spectra and calculating and just using the mean method. We're going to determine that we're going to just output the first 5 eigenvectors or calculate the first 5 eigenvectors associated with these data. So we will put n components equals 5. You yourself could take 7 or 10 or 20 or however many you want, but the more that you generate, the slower it's going to be. And then we are going to set up the PCA application for the randomized PCA. So it's going to allocate all the appropriate memory and set up the data structures. And to do this, we tell it we want n components minus 1. We're going to plot 5 components, but the first component that we're going to plot is going to be the mean. Now, if I want to actually look at the inputs to PCA, I can just do PCA question mark as before, and it takes in the number of components. So the maximum number of components, the default, as it says here, is 50. We're only going to use 5 because it's quick. And then you can whiten the data. And there's different options in terms of how you actually want to set up the random state of this randomized PCA. And we won't go into the details of that for now. And then it also gives you a nice example of how to actually apply this, this algorithm to a generic set of data. Right. And I haven't done this before, but let's see. Yes, and you can also go in and actually look at what the code is doing. And it's actually beneficial to go through some of these codes to see how they're actually setting up their problem, how they're actually deriving their PCA algorithm. And the other nice thing about it is they tend to also come with the actual reference, with the references directly back to the paper from which they implemented the algorithm. And so then you can actually go back and actually read the kind of pedigree and the history associated with the algorithm. And the second thing that you can see that's kind of nice is most of these applications, the principal component application in particular, is small. It's only a handful of lines of code, and so you can actually you can look at the data at the code, and you can follow it along, right? So it's relatively straightforward. Some of the applications, such as local linear embedding, are basically wrappers around C and C++ code. And so it's harder to actually follow the guts of the application. But for a lot of this, it's relatively straightforward to understand what the Python code is doing. All right, so we've set up the PCA. We've downloaded the data. The natural thing that we want to do is to fit a principal component analysis, or apply a principal component analysis to the spectrum. So for the case of PCA, all we do is we type PCA.fit, and then we give it the data that we're interested in, spectra. You can see it doesn't need to know about the wavelengths. It doesn't care about the wavelengths of the data. You can give it an arbitrary a vector. You could actually randomize that vector as long as you randomize all of your input vectors in the same way. So if you shuffled all in each one of the input spectra in exactly the same way, and you ran the PCA, and then you unshuffled at the end, you get exactly the same eigenvector. You get exactly the same eigenvectors out. So it doesn't care about the ordering of the data. Okay. So I now have a principal component analysis. I've done the fit to the data. And so naturally what I want to be able to do is to look at the actual data and look at the principal components. So if I do PCA, let's see, D is PCA, you'll see that if I take the specific PCA application, then there is associated with PCA is the components underscore. Each one of these components corresponds to the individual eigenvectors. So let's combine those eigenvectors together with the mean spectrum, and then we'll plot the mean spectrum and then the first, second, third, fourth, and fifth component. So we can combine these together to generate the PCA components simply by combining the mean spectrum, because remember when we did the PCA automatically subtracts out the mean for us, and then we want to take each one of the individual eigencomponents, so that will give us 4 eigencomponents coming out. We want to combine these together into an array, and that array we want to plot up at the end. So to do this, we just use NumPy, and we just use VStat to combine this first spectrum with this array of spectrum. So now we actually have a set of spectra. Let's see what this looks like. Actually, PCA components.shape. And you can see we have 5 spectra. So the mean, the first 4 principal components, and each one of these spectra is 850 elements long. So I've been saying all the way through this that you can't just apply these as a black box. You actually have to look at the data itself. So we'll generate a figure, and this figure will plot up the individual spectra. And we'll be able to see the mean, first, second, third, fourth eigencomponents. So let's loop through the number of components. So we'll cut and paste this, but let's talk about what it's going to do. We've generated a figure, and what we're going to do now is we're going to iterate through the 5 components, the mean and then the first 4 eigenvectors. We're going to, for each one of these components, we're going to generate a subplot, and then what we're going to do is to plot the wavelength against that principal component. Right? And so if we cut and paste this, should. Let's see if it works. I'm going to get rid of that. There we go. Does everyone get this plot here? Anyone not get this plot? Excellent. So, what do we have here? This is the principal components. First, this is the mean spectrum. This is the first principal component, second principal component, third component, and fourth component. What can we see from this? We can see that this is just the mean spectrum of all the input. The first principal component has, I think, has about one zero crossing. You should be able to see there. It is completely arbitrary whether you scale this multiply this by plus or minus 1. Okay? So you can flip that. Right? It doesn't matter because if I project a spectrum down onto these components, if I flip it, then it would just change the sign of that coefficient that we talked about. So in reality, the visualization of this, how you should display these eigencomponents, should just be a way that you can actually interpret them visually. Right? So this doesn't look like a real spectrum because the emission lines are in the negative direction. If I multiplied it by minus 1 and flipped it up, then it would look much more like a spectrum. So we can see in the first eigencomponent you have a lot of continuum emission. You have let's see, if we flip this, you'd have a positive red part and a negative blue part. So what's going to happen if I add these two components together, then I'm going to be changing the continuum, and I'm going to be changing the emission lines. And what should happen when you're looking at the principal component analysis is that as you add in the first eigenvector, you should increase the amount of, as I add in more red light, I should be decreasing the amount of emission lines that I see. And so this kind of comes back to does it make sense from a physical aspect? So does it make sense that if I increase the amount of light at wavelengths greater than, say, 4,000 angstroms, that would suggest it's a red spectrum, suggest it's an elliptical-type galaxy. Elliptical-type galaxies should have smaller star formation, and therefore you should have smaller emission lines. And so if that relationship is there, that increasing the amount of infrared light, increasing the amount of red light reduces the amount of emission lines, it makes physical sense that these eigencomponents are actually correlated with what we're seeing. The second thing you can see here is that the emission lines themselves, after the first component occupies a lot of the continuum, the second, third, and fourth components, and as you progressively go further down in terms of the eigen bases, you'll find that they look at more and more of the high-frequency information. And that means that you're looking more and more at the emission line information. So the first few components will describe the continuum. The eigenvectors after the first few are going to describe more of the emission line properties of the sources. Okay. But you can see, I mean, what we've done in 3 lines of code, 1 line to actually read the data in, 1 line to initialize the principal component analysis, another line to fit the eigenvectors. We've automatically generated a set of PCA components. So 3 to 4 lines of code to run principal component analysis with Python using scikit-learn. And I think this is the strength of all of these different techniques. And what we're going to do next, we're going to demonstrate this by using the same data and now applying a different technique, which is the independent component analysis. So remember, independent component analysis is the cocktail party problem, which means that I'm going to try and find a series of independent spectral components by maximizing the non-Gaussianity between those components. All right. So let's do this, and we'll do independent component analysis. ICA. So we're going to take it from decomposition again, because that's where all of these codes are housed. We're going to use fast ICA, which is one of the standard packages, or it's basically the standard fast implementation of independent component analysis. We're going to import it. We're going to set up or initialize fast ICA. And when we initialize it, we're going to ask for the same number of components. So we're going to look for 4 components coming out of this, in the same that we did with the first 4 eigenvectors out of principal component analysis. We're going to fit the independent component analysis. ICA actually is dependent on the ordering of the data. And that means we actually we transpose the matrix that we've been using for the principal component analysis, which didn't really care. Okay. So let me run apply ICA. Same structure as before, ICA.fit.spectra, but this time we've transposed the matrix instead of 850 by 100,000, it's now 100,000 by 850. And then we're going to extract out the components themselves. And we're going to combine them as we did before, just using NumPy to stack up the mean spectrum together with the independent components. And because we transformed it the first time, we have to transform it back when we're packaging these independent components together. So again, it's fast. And now the next thing we're going to do is just to plot these up. So we will loop through each one of this array, ICA_comp, which just houses the actual components, and we'll plot them up in the same way that we did with the principal component analysis. And if we do that, we should get a new spectrum where these components are overlaid on top of each other. So green, I believe, corresponds to, actually green corresponds to ICA and blue corresponds to PCA. So you get the mean spectrum, which is the same for both of them. And what we can see, and we'll do a better plot in a second, but what we can see is that well, it's difficult to see because of the scaling. So we'll do something slightly better in a minute. But you can see that the components are very similar to one another, as I showed you in the lecture, with just slightly different ordering. Yours look different from this? Let me kill this. So what I'll do is, let's see if yours look similar to the following. So we're just going to step out of this IPython, and we're just going to run all three together. So this is going to be principal component analysis plus independent component analysis, and then non-negative matrix factorization, which I didn't have a chance to talk about when I was going through it. We'll run all of these together, and while we're running them, it'll take a couple of seconds for it to compile it, and then download the data, apply it to the data, and so on. So has anyone got any questions so far about what we've been doing? Has anyone tried out putting in n_components that's different from 5? Does anyone want to try doing that? Why don't you try a different number? Because then you can actually start, particularly if you put in 10 or 15, then you should be able to see that the lower order components, the eigenvectors with smaller eigenvalues, right? The 10th, the 11th, the 12th eigenvector should show more of the emission lines and the absorption lines as opposed to the continuum. Right. So this is running all three together using exactly the same the same spectra. Shows you the mean spectrum. Non-negative matrix factorization doesn't require you to remove the mean because it's looking for a series of non-negative components. This technique was first used by Mike Blanton on SDSS spectra. So what it's doing here is we're showing you the principal components, the independent component analysis, and the non-negative matrix factorization. So you can see the main spectra are the same for between PCA and ICA by default. Are these the set of spectra that you're getting out from your analysis? No. We should look about this when we get into more of the hands-on part. But the two sets of spectra that you see, the components are fairly similar. Right? So this looks like this. Right? This looks a lot like this. The emission lines are similar from here and here. And so they're pulling out the same sorts of structures, which makes sense because they should have the same underlying stellar populations and emission lines. But you can see they're sensitive to slightly different things. For instance, the ICA, in general, when you go beyond the first few, will be much more sensitive to pulling out the emission line profiles as opposed to the having a mix of the continuum and the emission lines that you can see throughout all of the PCA components. Right. Okay. So we'll stop there for a second, then we're going to start out on local linear embedding and how we can run LLE. And we'll talk a little bit about the differences between how we run LLE and how we've run principal component analysis. But you should see that, again, same set of data that you can pull over, very easy to actually apply these techniques. You could actually walk through all of the decomposition packages inside of scikit-learn and try them out on the data. It's easy to actually apply it. It takes time to think about the results and what they mean. And one of the aspects that we haven't talked about, well, there's two aspects that we haven't really talked about in any of the applications. One aspect is that when you look at machine learning applications, and this is particularly true for density estimation techniques, and less true for the decomposition and the projection down onto a lower dimensional space, is typical techniques, so single sport vector machines. It's trying to classify two sets of data or data into two or more relations. The technique, when you actually look at it in the literature, it will show you a set of points looking like this and another set of points looking like that. So two Gaussian distributions. You will apply the machine learning application that is trying to segregate between these two populations. It will draw a nice line, and you will see this wonderful classification. That, unfortunately, is not really the astronomical data set. The data set that we have is typically a nice cluster of points here and another nice cluster of points here, and you want to separate out those two components. So you have to be thoughtful about how well you can apply these techniques. You can still actually do it. There are techniques out there for linear discriminant analysis that allows you to do a probabilistic, or other techniques allow you to do, or I guess based on density estimation, and this was done for the quasar populations, that allow you to do probabilistic separations between different classes of sources. But you have to be careful about whether the technique that you're trying to apply is applicable to your data. Second issue is also that the spectra that we're working with, at the first spectrum that we plotted up looked like this. It was this nice, beautiful spectrum. In reality, that spectrum looked like this. And this is because these regions here were skylines. And so we masked out the skylines, and we interpolated across the skylines, or there was a defect over here around the dichroic with splitting the red and the blue light, and so you can get within the data. And so quite often you have to do a significant amount of work to make things less sensitive to outlier populations or defects in the data. One way of doing this is if you're masking out regions, you can either account for the mask in your analysis, you can interpolate across the data, and you can interpolate both using principal components or with simple linear interpolations. We don't have time to go into that, but there's a fair amount of literature out there about how to correct your data for missing data points. And actually in the AstroML packages, when we load in the data, quite often we're fixing up the missing data sets. We're fixing up the masked regions by using principal component to interpolate across the spectral regions. So you can, I'll show you this in the next couple of applications. So in terms of projecting down onto principal components, for example, we do have a weighting function that weights in the projection, weights by the noise or the variance within the data. And the way we usually work with that is when there's missing data, we set the variance to a large number. And that's how we can downweight the poor spectral regions or the low signal to noise regions. In general, a lot of the machine learning applications that are optimized for speed assume that the noise is constant across all of the data, or that it is well defined, that you know that it's a Gaussian noise or Gaussian variance. And the reason for that is because of optimizing the algorithm to make it faster. So for density estimation here, the majority of the techniques for doing density estimation, such as fitting Gaussians to this distribution or mixtures of Gaussians, will ignore the fact that these points can have noise associated with them. There's some modifications to these techniques that will fit the Gaussians, allowing for noise or variance within the likelihood fit. But in general, most of the off-the-shelf applications ignore noise. So let's move on to manifold learning. So this was the LLE. So this was how do you analyze data looking at the local neighborhoods. So we'll import this from scikit-learn, and this is manifolds, and we said that when we were calculating the manifold, we had to calculate the number of nearest neighbors. So we're importing two things. One is the manifold learning application, and the second thing is an application that will find a series of nearest neighbors using trees to do that rapidly. It uses ball trees. This was written by Jake Vandenplas, who's a graduate student at the University of Washington. And this is what I was talking about in the first lecture, where I said, as we build tools that extend scikit-learn, it's important to put them back into scikit-learn. So if you develop a technique that's using local linear embedding or some new machine learning, it is useful for scikit-learn as a project, but it's also useful for us as a community that these techniques get put back into these generalized packages. Because then everyone benefits, and people can actually improve the algorithms and improve the speeds on the algorithms. So local linear embedding depends on two aspects. One is we have to define the number of neighbors we're going to consider when we're generating the weight matrix to predict the position of the point within this high-dimensional space. And the second thing we have to define is what dimensionality are we going to project down onto. So this isn't like principal component analysis where you can just do single-value decomposition and get all of the principal components. This is where we're going to say we want to take a high-dimensional space, a 4,000-dimensional space, or in this case, 850-dimensional space, where that corresponds to each one of the wavelengths, and I want to project that down onto 3 dimensions. So we'll specify the number of neighbors, and we'll specify the number of dimensions. And what you should think about is, as I increase the number of neighbors, it isn't just that I'm going to increase and add in more points from the surrounding neighborhood. I'm also going to make this slower, because I'm going to have to search for the number of nearest neighbors for every single point. So for every point within the data set, we're finding the 10 nearest neighbors in this application. Right, so we'll read in the data. In this case, we're using corrected spectra. And in fact, what we're going to do here is we're going to read in the data spectra. We're going to read them in as corrected, as we did before. And this means that we're going to read them in so they're all at the rest frame. So they've all been effectively shifted to redshift 0. And the second thing we're going to do is we're going to reconstruct the spectra. And we're going to reconstruct the spectra by using the principal component analysis. So what this is doing is it's taking each individual spectrum, it's projecting it down onto the eigenvectors, it's calculating the coefficients associated with each one of those eigenvectors, it's using those coefficients to reconstruct the spectrum, as we showed in the actual lecture. And then in regions where there's bad data, it's replacing the bad data regions or the mass regions with that reconstructed spectrum. And the reason that we're doing this is because local linear embedding is very sensitive to outliers. And the reason for that, as we talked about very briefly, is that if you imagine I have a set of points that is on a plane, and I'm looking at all of the local neighborhoods, effectively what I'm doing in the first step of principal component now of LLE is I'm looking at the local surface. Okay? And I'm hoping that all of these local surfaces will reproduce the overall manifold of the data. Right? If I have an outlier up here, then this is going to bias or tilt that local surface. So I'm very sensitive to outliers. I'm also sensitive to missing data. For instance, if you were looking for a manifold and you had a set of data that looked like this, which was on a nice plane, and then you removed all of the central points, it's going to learn a very different manifold than if you have a complete data set. So if you have data, it's difficult for LLE to map out the correct surface or manifold.
Can you only inject the interpolated spectra in regions that are bad or missing, and then use the original data everywhere else, or does it replace all the data with the
In this case, we're actually reconstructing the whole spectrum. So we're replacing the whole spectrum with a filtered data set. But in general, when you're doing this from a scientific application, the reason we're doing that is because we don't want very noisy spectra, because it makes it harder for us to show the local linear embedding. But in general, you only replace the bad data, the mass data. I think in the one that in this example here, when we reconstruct the spectra, I think, well, actually, why don't we actually look at the code? So what we're doing here is, let's see, reading in the data. We're making a copy of the spectrum for the reconstructed spectrum. We're recalculating the spectrum, and then we're taking the reconstructed spectrum. We're only populating it for the mass. So actually, in this case, we're actually just replacing the mass, the regions that the mass bits are set to bad. So we're just fixing up the bad regions of this variant. But when on a number of occasions we've done previously, we've used principal component analysis initially to filter the data to get rid of some of the noise spikes in the data. In which case we replace the whole spectrum with the linear combination of the eigencomponents. Right. Okay. We'll set up the color, because we're just going to color some of these points. And we're going to color them based on their line index classification. And this is just a spectral classification from the SDSS that's being measured based on identifying individual emission lines and looking at the ratios of those emission lines and using that to classify the galaxy or quasar spectrum. And then the next thing we're going to do is to run LLE. So we will set up LLE initially in terms of allocating all of the arrays that are required. And now we're going to run LLE. And you can see it's very similar to what we did before. We allocate all of the memory. And then what we do is we just apply the transform itself to the actual spectra. And this is going to take a few minutes, because what it's going to do is for every point in the data set, it's going to calculate the 10 nearest neighbors. From those 10 nearest neighbors, it's going to calculate the weights that will reproduce that individual point. So it's going to do, it's going to solve matrix operations, effectively fitting the surface at that point. And then it's going to take each of those weights and build up a sparse matrix for which is of size number of data points by number of data points, okay? Where the elements within that matrix correspond to all of the weights. And then it's going to do single value decomposition on that sparse matrix to project each point down into this lower dimensional space. So that takes a little bit of time to do that. Fortunately, I was speaking for long enough, so it's actually completed it. So now what we can do, we've done the transformation for each one of the input spectra, which has 4,000 or 850 wavelength components, we projected it down to 3-dimensional space. You should be able to try out changing the number of dimensions. Maybe you want to project it down into 4, 5, 6 dimensions, in which case all you will do is to change out_dim, or you may want to change the number of neighbors that you're working with, in which case you're just going to change n_neighbors. Okay. So we can plot up these data. So the coefficients that we're going to plot are going to correspond to the output of the LLE, and the color of the points that we're going to plot are going to be the colors that we define based on the line indices. So in order for this to work, we had to import LLE func, which just has these plotting routines in it. So what I want to do now is just to take these coefficients and to plot them up in a scatter plot. So let's do that. We have to import this first, and then we're going to plot up the coefficients, and let's see what we get. Okay. So these are the points of our few thousand spectra that we've read in. So the colors of the points, red corresponds to broad-line quasars, orange corresponds to narrow-line QSOs, corresponds to emission-line galaxies, blue corresponds to absorption-line galaxies. This is kind of the classic plot. So we're plotting, we remember we projected everything down onto 3 dimensions. So now we're doing a series of scatter plots that plots dimension 1 against dimension 2, 1 against 3, and 2 against 3. And so these are the clustering of the points within that space. And so looking at this, we can see a couple of things. One is that objects with a similar color cluster within this space. So the emission line galaxies all cluster here. The standard quiescent galaxies cluster around the outside of this. It's hard to see this because of this plot, because of the scaling, but the broad-line quasars separate out as well. But the second thing you see is the outliers in here. So the question is, how can I actually calculate those outliers? Because in some ways, those are the anomalies that we talked about right at the end of the lecture. And maybe I want to identify those anomalies because they're either going to tell me there's something wrong in the processing of my data, or they're going to tell me that I found some new class of source that I might want to investigate in more detail. So we can actually identify those outliers, and we can do this and just flag them. And we can do this by looking at the distance of each point from its set of neighbors. And if we calculate the distance of each point from its nearest, say, 10 neighbors, then we can identify sources or objects that are significantly away from the kind of the average locus of the data themselves. So let's do this, and you can do this just with this function called LLE func.flag_outliers. It takes in all of the coefficients, and it says, I want to identify the n sigma outliers, where these outliers are simply points that have a large distance away from their relative neighbors. And we can look at this by just looking at the code. And so it's straightforward. Uses a ball tree. We don't have to talk about ball trees. You've heard about different sorts of trees. Ball trees are trees that work well with high-dimensional data sets, as opposed to KD trees, which work well up to couple of tens of dimensions. Ball trees work to very high dimensionality. What it's effectively doing is finding all of the distances to the points, and then it's calculating the standard deviation of all of those distances. And then the last thing it's doing is it's finding all points that are n sigma greater than that standard deviation. So it's just finding the outlying points. And you could do this, you could change this to find all points, a percentile of points with the largest distances. So you could find maybe the 10 largest distances or the 10% of largest distances just by changing what we actually return here. It's just a way of flagging outlier points. So if we want to identify those points that aren't flagged, then what this is going to return is an array where it has true, 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 false, true, 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 false. And so just by applying this array to the data, we can actually select the points that, in this case, aren't flagged. Okay. So flag returns true for a point that is more than 0.25 sigma standard deviations away from the overall distribution of points. And this 0.25 was just made up because it gives us a nice plot. There's nothing fundamental about why we chose that. And so by doing the complement of that, we're returning all of the points that aren't more than 2 sigma away. 0.25 sigma away. And so we're trying to return all the points within that, within the locus of galaxies. If we do that for the actual coefficients, we should do it for the flags as well. So because we should do that for the colors as well, because we want to have the arrays identical. And then we can plot up this plot again. Okay, let me actually kill that and redo it. So now what we've done, so you may actually have to, because they'll overplot on each other, and so you won't be able to see it. Just deleting the figure and rerunning it is the solution, or you could make a separate figure, a new figure too. And see, now what we've done is we've excluded all of the points that are large outliers, and is effectively all we're doing now is zooming in, and so you can see the blue galaxies are here, the emission line galaxies, so the quiescent galaxies lie around here, the emission line galaxies reside around here, and it is difficult to identify the broadline quasars because there's so few of these in the data set. But again, now see that quiescent and emission line galaxies are separating themselves out in this two-dimensional space. What other aspects should we be aware of this? Well, for LLE, it's slow, and so typically you won't run it on 400,000 spectra. You may run it on a few tens of thousands of spectra. And so you need to choose the right spectra to work with. And typically you don't really want to choose just a random sample of spectra, because most of the sources or most of the spectra, if you just take a random sample, are going to look like the average spectrum. And if I want to learn what the manifold looks like, I really want almost a smooth distribution I want to have a smooth coverage of all of the parameter space, or an even coverage of all the parameter space, because I want to map out what the manifold looks like, not just to focus on the region that corresponds to the average galaxy or the average spectrum. And so you have to be careful about how you select your training sample. And there are many different ways of doing that. There's a paper by Jake van der Plas that talks about these different techniques. If anyone's interested in that, afterwards I can point you to that paper. The idea is effectively that as you add in a new object into your sample, you determine whether it provides you additional information about the surface. And if it doesn't, you don't bother adding it. And if it does, you added it. The second thing you have to be careful about is as you add in points, you want to make sure that they're not too divergent from the overall manifold, because they may just be junk, and you don't want to add junk into the data. The last thing is the LLE that you derive, or the manifold that you derive, may be dependent on the sample that you use for your classification. So while once you've defined what this manifold looks like, you can take another spectrum and drop it in and get a new classification out. And that doesn't necessarily mean that if I take one sample of galaxies and then I take another sample of galaxies, that I would get, and I derived an LLE classification on this sample and another LLE classification on the other sample, that classification would be the same. You can derive different manifolds from different data sets. So you have to be careful, which just really comes back to the idea that you have to take a representative sample of data. And I think that's it. So that goes through all of the basic steps. We've done principal component analysis, we've done independent component analysis, we've done local linear embedding. So we did the different techniques that we talked about in the lecture. We've gone through very briefly, a quick way of identifying outliers, so a way of classifying anomalies, so you could apply that to the data. What I thought we would leave here as an exercise for maybe this afternoon and maybe tomorrow morning, and if you run into any issues, I can help you out with these, is to see whether you can reproduce. We've effectively produced, let's see if I can do this. We've effectively produced this figure here, which was the LLE implementation. What I'd like you to try and do is to reproduce the equivalent, but now for the principal components. And I showed that in the lecture. Which is this one. So that would be taking the input spectra, projecting them down onto the eigenvectors, getting out the coefficients, and plotting up the coefficients using the same plotting package that we did for the this LLE func plotting package that we just did for the LLE points. So that would be one exercise to do. And that will show you that the classifications that you get for the principal components are much more, there's much more scatter or coupling between the emission line and the non-emission line galaxies. It's harder to discriminate between them. The other thing that you could do is to experiment with different numbers of components coming out. So numbers of LLE components, you might want to plot the first 6 components, and varying the number of nearest neighbors as well, to see how that distribution of points, how this manifold that you've learned is going to change as a function of the number of points. So why don't you try and reproduce the PCA figure, and I will give you a hint associated with this. To generate the principal component analysis figure, you need to generate the eigenvectors, which is what we went through, to generate those components. Then you have to take each one of the spectra, and you have to project that spectrum down onto those principal components. So you have to do a dot product between the spectrum and the eigenvector, and that's going to give you a coefficient. That will give you a series of coefficients, and then you can plot those coefficients using the LLE func spec underscore component underscore plot. Okay? So why don't we try and do that over the next 10, 15 minutes or so, and this afternoon. And if you run into any problems, just come and stop by me. And we'll go through those, and I'll wander around the room while we're doing this. And if you want to look at some other techniques, density estimation on the scatter plots, maybe running density estimation on some of the galaxy models that you've been doing, we can try that out as well. Okay, thanks.